bilmediğim şeyler olduğunu gördüm. Doktorasını 2006 yılında School of Mechanical Materials and Manufacturing Engineering and Operating Management bölümünde, biraz uzun bölüm, University of Nottingham'da kendisi alıyor. Ondan sonra postdoc çalışmalarında Rolls-Royce Technology Center'da devam ediyor. Orada birçok destekli endüstriyel ve akademik projelere el atıyor. Türkiye'ye geldikten sonra elbette hani birçok TÜBİTAK ve özel sektör projelerinde yer alıyor. 2007-2015 yıllarında Gazi Üniversitesi'nde çalıştıktan sonra 2017'den beri kendisi Gazi Üniversitesi'nde makine mühendisliği bölümündesiniz değil mi? Evet. Şu anda profesör olarak devam ediyor. Kendisi Gazi Üniversitesi'nin aslında eklemeli imalat ya da Advanced Manufacturing Technologies Research Group'un başını çekiyor. En önemlisi son yıllardaki en güzel çalışmalardan biri, benim de takdir ettiğim, kendileri Ulaş Hocam ve çok güzel bir ekiple birlikte Ekleme İmalat Derneği kurdular. Ve hani bu işin endüstriyel yanından yana ekleme imalatın bence özellikle işte 3 boyutlu 3D printing gibi teknolojiler zaten endüstri ve aslında bütün toplumu şekillendiriyor ve bu konuda ülkemizin işte Ulaş Hocam ve Oğuzhan Hocam gibi hocalar sayesinde çok önde gitmesi açıkçası beni de ciddi anlamda gurur veriyor. Kendisi Gazi Mühendislik ve Mimarlık dergisinin kendisi endeksli bir dergidir. Hatta çoğu uluslararası dergiden çok daha da iyidir. Ben de yardımcı editör olarak kendisine yardım ediyorum. Baş editör olarak çalışıyor. İnanılmaz zor bir iş. Gerçekten hiçbir şey yok, karşılığı olmayan, kimsenin takdir etmedi ama çok önemli, çok zor ve gerçekten önemli bir iş yani. Hani bu zor bir alanda endekse taşımak ki çok ünlü bazılarının dergilerin endeksten düştüğünü duyuyoruz son zamanlarda. Kendisi ayrıca başka dergilerin editörlüğünü yapıyor. Geçen Oğuzhan Hocam da Metal Worm, işte burada da bir miktar anlatacak, firmasının yaptığı işlerle ilgili bir toplantı yaptılar. En son ben dedim yani hani biz ne yani hani biz bir şey yapamayız size. Gerçekten çok etkilendim. Çok güzel işler yapıyorlar. Yani hem Metal Worm hem de Metal Worm bağlı olduğu ana firma teknoloji anlamında hani dediğim gibi çok büyük firmaların çok önünde, gerçekten ileri teknolojide iyi işler yapıyorlar. Hatta bir tane yüksek lisans öğrencimin de oraya gitmesine de çok sevindim açıkçası. Şimdi sunumunu dinleyelim. Ben kendisine geldiği için çok teşekkür ediyorum.
Çok teşekkür ederim hocam. Evet hocam. Tabii ki. Bu tamam değil mi?
Evet, o çalışıyor.
Okay, thank you very much, Mert Hocam, and thank you very much for inviting me and to you and especially for ROMER. And I'd like to hi everybody, to all, and here and also in the Zoom. Basically, my presentation is about additive manufacturing, but my focus main on metal. And also, I like to make a link between the ROMER. So therefore, in my some research works, I'm going to actually explain how we use robots in our research studies. And also I'd like to give some very small highlights on what will be the novel research trends in additive manufacturing. I'm sure that you all hear about additive manufacturing, but actually in our mechanical engineering side, we a bit focus on some cases. I got lots of administrative and some academic duties. As Mert Hocam said that actually I graduated from Gazi University and I got PhD from Nottingham University in Rolls-Royce UTC, and also I did my postdoc in here as well. And then I come back to Gazi University and now I'm a lecturer and professor in Gazi University. And I got some, as I said, administering some academic duties in TÜBİTAK, some, the journal. And also I'm the CEO of the Metal Worm as well. And also we are now an association. I'm the current president of this association at the moment. We are organizing AMC conference. We organized the 4th AMC conference a few weeks ago. And so this is what we do actually as a researcher. Well, basically, I'm sure that you know all about the 3D printing and additive manufacturing, but actually we compare with the subtractive manufacturing. Basically, we add material, not remove material. So therefore, When we compare to the subtractive manufacturing, we use less material, because in subtractive manufacturing we actually remove some material from the stock, the geometry. So therefore, the main difference between the subtractive manufacturing and additive manufacturing, we may say that we are using less material than the subtractive manufacturing. The steps, how we use the steps in manufacturing, basically at the beginning we have a CAD data in 3D model, and then we try to have a STL file which is having basically some data, like the coordinates and the face normals, etc. And then we have to do some slicing operation, that's because this is layer by layer manufacturing, so therefore we have to have some information on each slices. And then we have to generate the machine codes, and then we send all the machine codes to the machine, and we get the production or the produced part. So when we compare to some conventional process, basically we omit maybe lots of steps. So therefore this is called as direct manufacturing, direct digital manufacturing, and rapid manufacturing, and different names actually we can give it. But at the end of the day, we will have basically smaller or less lead time when we compare to the conventional processes. Of course, we can do lots of classification on additive manufacturing, some of them technology based and some of them material based, because we are using a raw material to produce the parts. So this is one of the the classification. This is mainly the material based, because some additive manufacturing technologies, they use liquid based materials like resins. Some of them use solid based materials, and some of them use powder or wire type of materials. But in fact, we are going to have actually at the moment there are 7 main additive manufacturing technologies are available, and they are commercial as well as they are the machines. They have the machines basically. The first one is the wet polymerization. Basically, we are using a heat source or a light to make the resin or polymeric material to make it curing basically. And we have material extrusion process, material jetting process. These are mainly polymeric materials as a raw material. And binder jetting, this is another technology. Powder bed fusion, which is mainly use the metal powders. And now the most actually mature technology in additive manufacturing at the moment. And direct energy deposition, and also the sheet lamination process. These are, as I said, 7 main additive manufacturing technologies. They are commercially used in the industry at the moment. As I said, different the mechanisms and different the manipulations are used to make the 3D parts. When we use the material as polymer or composites, basically we either use light, laser, the ink to make the 3D the parts. But in the metal side, so we have to have some energy source. And we use that energy source mainly to produce the part or to melt the metal. Either it could be the powder or wire. So it could be the laser or electron beam or arc, or in some cases. Well, basically we have to have a large heat source to melt the metal, because the metal melting temperatures are higher than the polymers. So therefore in metal side, basically we generally prefer to have some some high heat sources. Of course, basically when we compare to each additive manufacturing process, there are some advantages and disadvantages between each other. For example, when you take a look at if you would like to to produce a complex geometry, for example, powder bed fusion process gives high rate of complexities, but on the other hand, for example, WAM, which is wire arc additive manufacturing, gives less complexity. But when you take a look at the part size, the WAM process may have more advantage, the position, build rates, for example, or platform flexibility, mechanical properties, so they may differ. So therefore, we choose the proper additive manufacturing process for our design considerations, and where we are going to use and what purpose that we are going to use, basically. Well, this is the latest maturity index of the additive manufacturing methods or technologies. This is the technology maturity index on the horizontal line, and the vertical axis is the industrialization index. So if you take a look at in here, the laser powder bed fusion process, which we use lasers to direct to powder surface and melt it, and layer by layer we do melting. So this is at the moment the most common one, and also more commercial one. And EBPF, which is the electron beam powder bed fusion process, also has the actual largest index numbers when we compare the others. And WAM also is around here, and the other processes, as you can see, they're trying to be mature as much as possible. And of course, the researchers like you and us, we try to make them as mature as possible and to spread in the industry, to make them applicable in the real parts or functional parts. Well, if you take a look at the 3D printing market or additive manufacturing market, there is always a growing, basically, trends. The global 3D printing market is expected to be worth US dollars, actually 34 billion in 2028. And this is metal AM system sales, as you can see, basically, although in the pandemic year, there's going to be a bit drop, but actually it is increasing rapidly. And these are also in different sectors, as you can see, the 3D printing market always growing up. So therefore, there are lots of companies now, they're coming to the industry or the market. So there are lots of investment on the additive manufacturing as well. If you take a look at also the, some material side, mostly the polymeric materials are used as a raw material in 3D printing or additive manufacturing, and metals is the photopolymeric materials, and also metal is the third. But the metals is now more growing because the metal part is more functional than the polymeric part. We use the polymeric materials generally for rapid prototyping, but the metals are used for mainly functional parts. And these are some of the metals that we currently use in additive manufacturing, like stainless steel, aluminum. These are the most percentage, and also the titanium. Titanium is mainly preferred by aerospace and defense industry. Stainless steel is common, which is die molds, and aluminum is also used for die molds and for prototyping as well. But also there are lots of materials are getting some percentage from the use of the as a raw material, like stainless steel, Inconel, which is nickel-based alloy, and tool steel, some Hassel alloys, etc. Also, if you take a look at the systems which is installed, country by country, if you take a look at of course, North America, the United States has the largest percentage. They invest a lot, and also there are some, the contributions by the government as well. They urge all the companies to invest on additive manufacturing and 3D printing, because they see that, especially the United States, they see that this is the future manufacturing process, and that's why actually they want to be a leader in that market. So that, as you can see, United States has the largest percentage as AM system installation, and the China, of course, Germany, Japan. So we are here actually 11th. So yes, there are some investment in the Turkish side, especially research centers and the companies. But our position not very bad. But actually, when we compare to some of the countries, for example, Canada, Spain, Taiwan, and Korea, so basically they invest a lot. And probably in the near future, they will be in the some front position when you compare to Turkey. Okay, so these are some other, how the 3D printing research contribution actually, as you can see, the years, also lots of papers are, seen on the journals. So it's a hot topic trends in the, the research, and also academic paper as well. And so, okay, so that's it. Well, so I'd like to now mention about what we do. I have a research group which I call as AMTRG, Advanced Manufacturing Technical Research Group. When I come back from the UK, so I founded this research group. So this is mainly by, the members of my research group is mainly by my MSc, PhD, and postdoc researchers. So what we do basically, I have almost 20 students, some of them postdoc and some of them PhD and some of them MSc students. Few of them are staying with me and some of them from the the companies like Aselsan, Tusash, Roketsan, etc. And I have also some postdoc researchers as well. Some of them my former PhD students, but I have also 2 postdoc researchers with me as well. What we do basically, we mainly focus on the metal additive manufacturing and additive manufacturing. So, for example, in my one of my actually research work, we mainly focus on how laser interact with the powder, because when we produce the parts, mainly we have to melt the metal. So, in melting process, we use a heat source as laser, but how laser interact with the powder and how a melt pool is going to be produced on the metal surface or the layer, and how can we actually get the proper process parameters in order to obtain high quality parts. This is one of my research work, and that research work basically contains some multiphysics, like we actually sometimes try to derive some thermal actually equations. We sometimes deal with the metal powders. We sometimes deal with the laser. So therefore, this is multiphysics. And in another works, actually, we try to actually determine that because when the laser interact with the powder, it melts the powder. But the molten powder is going to be solidified in very soon, actually in milliseconds. So therefore, how the faces are basically the core of the mechanical properties. So if you control the faces, so you may control the mechanical properties. So therefore, in this PhD work, we try to control the faces during the solidification, and the final aim is, of course, to obtain the proper parameters and proper condition, and also plan the process in order to get the proper and also the best quality parts. And of course, on the additive manufacturing, actually, the surface is not good because we use powders. So the surface, when we take a look at the closed loop on the surface, as you can see, here is the as-built surfaces. Surfaces are having large surface roughness. I mean, there are lots of waves. So we do not like it because as a mechanical desirement, basically, we need to have some, the very smooth surfaces in order to have some mechanical properties. So we search how we improve it. And then one of them is laser. So we use laser to make a remelting on the surface and to polish it as much as possible. So this is the new technology, actually. We tried actually a couple of times, and we did some few projects. And then also one of my former PhD students, actually, he graduated. Now he worked a lot on this topic, and we actually directed the laser and to make the laser beam on the surface and to make it a thin layer, the remelt area, and that thin layer remelt area is produce the smoother surface when we compare to the as-built surface. Then we call it as laser polishing. Of course, it is under research because we face some problems like cracks because of the high solidification, which we do not like it. So, but we still actually work on it. Another actually, my research work, basically we use WAM, which is we use robots, and then we use a arc heat source and to melt the wire and to produce layer by layer the part. And then we did a lot of, the mechanical, metallurgical tests and how we improve it and which kind of the process parameters that we need to use, which type of heat source also or heat input that we need to, actually give to the material to make the proper condition on the parts. So therefore, we did a lot of tests. One of my research work, again, we work on some truss-based geometries, and in that case, we use some biomimicry approach, and then we produce some, as you can see, truss base, the geometries, and then to actually make some mechanical tests. Basically, we use some compression tests, and then actually we measure the stresses and the strain and how it actually behaves under loading, because it could be used for some, the implants, like knee implants. Okay, so we need to have some kind of, the absorption of the energy. So therefore, we prefer to use such kind of geometries. In one of my work, again, we work on some design approach. This is the conventional design parts, actually, although it is also topologically optimized, because as you can see, there are some, the holes in here. But actually, we work on it, and then we try to make it a new design for additive manufacturing, and then we produce that part, which is actually also be used as the bracket to hold the reaction wheels on the satellites. This is a project, basically, although this is the MSc work results, but we did a project, and I have some results as well. And I work in my research work, I work with Aselsan, one of my MSc students, and we try to design some parts which already assembled. That means the revolve joints, actually. I mean, we try to obtain the correct process parameters, and for that kind of revolve joints, and then actually, because for the revolve joints, there are two options. I mean, you either produce the parts individually and then you assemble it, actually, but you may also produce it as it is, or as a consolidated, the part. But we prefer the consolidated design, because it makes it actually more cheaper and also faster as well. And also in additive manufacturing side, it's a new area, because there are some, the gaps on that area, so therefore we focus on it. And also in another, my research work, actually we work, my students in Aselsan, and we work on the sheet metal lamination. We use ultrasounds actually to make the welding process, and then we use the sheets and to actually bond them by welding, which is called as microsound welding or ultrasound welding. So therefore, we can do some, the layer by layer manufacturing. This is the setup that we actually design and produce it, and so we try to actually use new materials and new sheets materials, and to make the, the ultrasound additive manufacturing. This is one of the maybe the unique work in Turkey, especially on the sheet metal lamination. And also we work on different designs, because I mean, as I said, I mean, in additive manufacturing actually serves new design approach. So therefore, since we have some, the flexibilities on the manufacturing side, we may have some organic shapes. So therefore, for example, this one is a bracket again, which is work under random vibration, and there are, the 3 or 4 parts, which are they produce, the individually and assembled together, but we produce it as a single part. So therefore, it is also a consolidated part. Then we actually did lots of, the random vibration tests, and to check it if it is, satisfy the requirements. Well, basically on the WAM side, which is wire arc additive manufacturing, which I use a lot, and also my company MetalWorm also focuses on WAM, but I started that work in 2010, which is the first work in Turkey. So we actually designed these, the very old-fashioned, the design, which I spent 10,000 Turkish liras to build it. But we first did work on the new, the attempts of how we built the metal layer by layer. And then actually we use robots because more feasible, and it gives lots of flexibilities. And this is a work that we actually work together with FNSS, which is a side project, and then we try to build some big size and large size parts by using robots and welding machine, as you can see. and also positioner. So therefore we actually, for this part of course, I mean only the robot is enough, or maybe the position is enough, but in many cases we actually have the 8-axis manipulation to produce the parts. We did lots of tests, mechanical tests, metallurgical tests, in order to actually prove that these, the process is suitable for production of the large-scale parts. And also we got some, the temperature measurements, because during the production we melt the metal, and so we apply lots of heat. That heat produces some distortions and some unwanted effects, so therefore we have to optimize it. And also I started work with integral robotic, which we actually started to work in 2015. And we decided that the one process, which is robotic based process, we need to have a machine. The machine should have some the hardware and software, but there is a need in the industry, because additive manufacturing is growing, and there are some attempts on the one side and robotic, the additive manufacturing, but there is no specific machine on it. So therefore, we actually started to work with Integro, and we submit a research project to the TÜBİTAK, and TÜBİTAK funded us. And then basically we developed this metal worm machine. And as you can see here, now we have a robotic system, a positioner system, and we have software on the offline side that we can produce robotic tool paths to create the 3D objects, as well as we have process monitoring software as well, because we need to get some data during the process, like voltage, current, heat source, heat input, layer height, etc. This is now commercial machine, so we try to sell it now. And also we do lots of production by using this machine. Basically, once we release this machine to the market, basically, and also at the same time in the world, there are 3 or 4 companies at the same time they release the same machine. So therefore, we may say that we all think about the same. And this is the process monitoring software that we use basically. As you can see, we collect all the data from the process, and also we have also a welding camera which focus on the mat pool, and also we can capture the temperature on the mat pool area, and it is very useful for us to collect the some data and to plan the process for proper and to best applications. And also as I said, we collect the data so we can create the digital twin of the part as well. And what we do basically, we got the current, voltage, Wi-Fi speed, heat input. These are some of the data that we collect. And then we merge with the coordinates of the robots, and then we can create that kind of digital twin of the parts. What we use for basically, in additive manufacturing, we actually do the manufacturing layer by layer. So in commercial manufacturing processes, okay, especially for aerospace and defense industry, they need some certification. And in that certification, you have to supply all the data that you use in your manufacturing process. So in additive manufacturing, you have to also give all the data for each layer. So in that case, firstly, we give all the the information or all the data, as I said, for process parameters for each layer, as well as we may check it for quality control as well, because you may have some intervals for each data, and if you are going to see some kind of the peaks, so you may actually check on your part and then see that what will be wrong on the process. So therefore, it could be used for quality control as well. As I said, actually on the robots, basically, first of all, we need to create the tool paths for the robots, and where the robots is going to have a position and to melt the metal and to create the 3D parts. So therefore, we are using an offline robotic tool path planning software. This is not our software, basically. We bought it, basically. But we work that company a lot because we give them feedbacks a lot. And then they actually improve their software as much as possible because there are lots of different geometries we work on it. And as you can see on this propeller as well. So it is not the 2 axis, 3 axis, it is in 8 axis in total when we consider the position as well. And we generally use step data to create the toolpaths, and because we have geometry or each feature individually. Basically, by using metal worm and robots, so we can create different functional parts. This is one of the oil and gas parts. This is one of the metal composite die parts, which we produce for TUSAŞ, Turkish Aerospace. And this is one of the propeller that we can use in also marine applications. In the WAM side and the robotic side, basically we try to work to improve the process as much as possible, because what we observe that we apply lots of heat. So therefore we have to control the solidification. So therefore we, in my research work again, my PhD work, we work with metal worms. So we try to make a heat barrier. So therefore we try to cool down the parts as slow as possible. Then we actually control the reduced stresses, we control the, the solidification and microstructure formation as well. In another work, actually what we observe that when you work, when it's small area, you apply lots of heat on it. So therefore it make some distortion, some wrapping and some faults. So therefore we try to actually make an adaptive toolpath planning on the robotic side. So therefore this is one of my, again, the PhD work with my students. So he actually developed an algorithm that actually sense where the heat is dissipated more, so then it actually produce another part of the, or another section of the parts, and they produce the layer and then come back again and produce some layers. So by doing that, we try to dissipate the heat as much as possible to reduce some distortions and so make the geometry as as neat as possible. And also I work with TUSAŞ and on some critical parts on the powder bed size basically, and also I work with TÜBİTAK Uzay, which we developed this the reaction wheel bracket, because on each satellite there are 4 brackets that hold the satellite to the platform. And these reaction wheel brackets actually they are having about 4.6 kilograms in weight. And then when we design it by biomimicry, actually we reduce it 1 kilogram less. So that means 1 kilogram in space application, that means $10,000. Or you may add more, the 1 kilogram. But if you consider that there are 4 brackets, so 4 kilograms, we save it. This is how we design it, process. But this is more important because in this case, once we design it, basically, we firstly consider that it is under vibration. We have thought that there are vibration, but this is sine vibration. I mean, the vibration is going like this or in sine wave, and then we test it, and then we got some the cracks on the surface about here, around here, and then we said that okay, there is something wrong on the design, and they say that did you consider the random vibration? We said that no, we didn't consider that. What kind of vibration is this? They say that yes, you have some kind of sine vibration, but in some cases you have the frequency may change, the amplitude also may change. So then we actually redesign it, reproduce it, and also we test it again, as you can see. So we shake it like this. So it's really actually the high level of the test. So as you can see on the heat, and now the part passed now. I work with Roketsan as well in the TÜBİTAK 1004 project. Basically, in this project, we actually try to generate the toolpaths on the sample part that could be used in the Roketsan, the defense applications. And the project mainly actually generating the toolpaths for the robotic worm, because they have the worm system as well. I mean, I started to work with Roketsan about 8 years ago, so they have 2 systems at the moment, and they, the highly work on the worm. On the surface side, we had a project with TI in Eskişehir. So actually, we again tried to reduce the surface roughness of the metal AM parts, and we used electrochemical machining. We actually removed the material in atomic level, and then we try to, as you can see, reduce the surface roughness as much as we can. And also we also work with Aselsan, again work on the laser polishing sites, as you can see here. So we try to reduce the surface nozzles as much as we can by, again, remelting on it. Well, this is a very interesting topic, and I'm the first, maybe the unique, the researcher to work on this this technology. And after completing this project, also TI interested in that project as well. And then we got 6 months research projects, and again we work on titanium aluminide, which is a very unique material. And then again we try to actually polish some surfaces, and also in that project we use robots to manipulate the laser heads, as you can see here. Although we generally prefer to make the laser polishing on the flat surface, but in this project also we focus on the form surfaces as well, which at the end of the day, which we try to actually polish the blade surfaces, because they like to produce the blade by additive manufacturing, but the surface is not good again, so they like to make it smooth as much as possible. These are some of the, as you can see, convex and the concave surfaces that we polish. Although, again, it's not a mature technology. Yes, it is under research. As you can see, there are, the patches, and so these lines are not actually intentionally left here, but actually we try to make the whole surface as polished and no lines like this. So we still work on it. And also on the laser side, we still continue on it, and to make some parts having high fatigue, the strength and life. So we work on laser shock peening. What we do basically, we have some additive manufacturing parts, and we send laser shocks, like the bombarding actually, and then we produce the compressive stresses on the surface. Then we increase the fatigue life. We did lots of tests on it, and this is one of my TI project again, and also my PhD students work on it, and he's about to finish his PhD. And we observed that we actually produce some compressive stresses, which are very beneficial stresses for improving the fatigue. And we work with the HiLace, which is a research lab in Czechia. So actually, it was a very good collaboration. We still work on the DAD side. So I work with UniqueTech to produce some function graded parts that we are aimed to produce some blades or aero engine blades, to using some, the differentiating the properties of the parts or materials, and different materials like stainless steels and alkaline, and to mix them. And also I work with Josh Gunner's company. They have also the robots and DAD systems, and this is the first part in Turkey that we produce by DAD process. And also this is a European project, and also the TUSAŞ was one of the partners. And this is how we produce this part. We design these parts, and then we make lots of the analysis and the tests. This is the near-net shape part, and afterwards, of course, this is going to be machined, and the final part is going to be used. And finally, also we are involved some of the European project like Erasmus, and in this project we try to make a syllabus for additive manufacturing course in European countries. So we almost finish it. So we have some now pilot groups that we actually give the lectures. Or to give these trainings, and to get some data on them. So this is now is almost finished this project. So I also involved some of the project with the industry like Ermaksan. We produced the first 3D printing part, printing machine with Ermaksan. This is the first part, machine. And then I also work with Estaş in Sivas. They also like to actually produce another 3D printing machine, and then we actually produce or they develop this machine basically. This is the second machine in Turkey in metal additive manufacturing. Well, we use robots in additive manufacturing a lot, basically, for manipulation mainly. We use 3D printing in construction, furniture, polymer, metal. We use a lot. And basically, programming of the robots and also manipulating of the robots, and also we attach some of the the cameras on it, some sensors, some lasers, and to pick the data. So basically the robots are very flexible elements, or the machines, or maybe the devices that we use in additive manufacturing a lot. Okay, so what could be the future trends in additive manufacturing? I mean, first of all, maybe you could be more familiar on that case. I mean, in macro and nanoscale additive manufacturing is still under research, research. So therefore, there's going to be some material jetting, some the writing, some as you can see, circuits and inductors, and writing some sensors and to collect the data from the parts. So it would be possible by using additive manufacturing. Again, there's some smart structures which I already worked a little bit on the ultrasonic additive manufacturing. What we do basically, we layer by layer actually put the sheet metal, we bond them by ultrasonic welding. But the most important thing is we may actually insert some gauges, some sensors on it, because in the other process, at the manufacturing process, it is almost impossible. But by using this technology, we could actually add some, the sensing devices. So therefore, once we produce the part like this, the part is going to be smart. I mean, sense it. I mean, also emit some information. Also give some information, take some information, data, etc. Basically, I mean, additive manufacturing is growing a lot. I mean, growing very fast. So therefore, lots of different designs, very complicated designs are available. Especially nowadays, the engines, I mean, the space and the defense industry very much focus on that case. So because you may not actually have such kind of design by using other conventional processes. This is the only process or technology is the additive manufacturing technology to produce that kind of, the detailed parts. And also bioprinting and the 4D printing is also another topic that we can focus on additive manufacturing. Basically, the 4D printing starts with the additive 3D printing, but also we may stimulate the geometry by light, by heat, or by magnets. And then there's going to be the fourth, the dimension may come. So therefore, this is another issue that could be worked. And there are few researchers actually in Turkey that they work on the bioprinting and also the 4D printing. In the MEMS, there are lots of alternatives, and the potential and the drugs in pharmacy, they are also using additive manufacturing, and medical side also. There are lots of the potential in additive manufacturing. As I said, aerospace and defense, they are very much interested because they like to build large parts, big parts, and metal parts, so therefore they invest a lot. And these are some of the examples. Again, for example, for example, Roketsan as well. I mean, the TUSAŞ or the other companies, they like to produce that kind of engine parts as a single production volume. This is one of the most complicated part that is produced so far by additive manufacturing. These are some other parts. And these are the one parts basically. One company in the United States actually they produce these parts as single parts. So therefore, actually this is another the potential of additive manufacturing to create such kind of aerospace parts. Okay, what could be some topics actually? Lasers, post-processing, shape member alloys, and the function graded parts, cold spraying, refractor alloys, and in-situ control monitoring is the good potential on it. Machine learning and deep learning, and the biomimicry, and also topology optimization, phase transformation could be there could be some the potential research topics that actually could be work on additive manufacturing. Well, I work with different companies. They sometimes actually give funds to me, and sometimes actually we work together. So therefore, actually we have some the good collaboration with them. And also I work with some other the universities in for example, we work with Bologna, Italy, Pittsburgh, United States, Tennessee Tech in the United States, Fraunhofer. Actually, they are very friendly on that case, and also Politecnica di Milano. We work together. So also we have an association, Turkish Additive Manufacturing Association. Also we organize the Additive Manufacturing Conference, and basically we are located in Technopark Istanbul, but me and Ulaş Hoca here. Also we have on the administrative side, Evren Tan from Aselsan, and Mustafa Safa Yılmaz from Uludağ University, and Emrecan Hoca from the İTÜ, and we have also other researchers and from academia and also from the industry as well. What we do basically as TAMA, we actually organize additive manufacturing conference, we organize some additive manufacturing days, some project days, and also we have the Turkish English term dictionary, we release it. And finally, actually we release additive manufacturing textbook. This is the latest. And a few weeks ago, we organized the AMC conference, and then from the 10 different countries, we had more than 270 participants attended the conference, and then there were 20 sponsors. Basically, it's very, the very busy conference when we, actually when we are actually thinking about that the academia and the industry. So that there was a very good, the chances for the the guys from the industry and also academia. So this is our textbook, which is in Turkish. We are planning to release the English, but it is a textbook now. So we recommend all the the people who would like to know about additive manufacturing. Well, thank you very much for listening to me, and hopefully it will be beneficial for you.